Alright, so in the last section of Chapter 5, we're going to talk about compositions of transformations. So basically, we're going to take a shape, we're going to apply all the transformations that we've known so far to get it like from point A to point B. There's a couple different ways that these questions can be asked, so we're going to look at an example of all three of them in this video. So first, we really got to understand the difference between being congruent and similar. Congruent means that you're the same shape and size. Similar means that you're the same shape but different sizes. So like here I have some some random shape A, B, C, D, E. I could shift it, I could rotate it. As long as I do anything that doesn't change the size of it, it's going to stay congruent. Similar shapes, though, I change the size of it. So I start with that same shape A, B, C, D, E, and I made it way bigger. Those would be similar figures. So something to remember is that to keep shapes congruent, I could translate, reflect, or rotate. To make shapes similar, I would have to dilate it, okay? So I could do any combination of translations, reflections, and rotations. It would keep shape 1 and shape 2 congruent. As soon as I dilate that image, they're similar. They're not congruent anymore. So in the first example, let's say I have a problem like this. Triangle MNO is transformed to produce triangle XYZ. Select all the transformations that would guarantee that the triangles are congruent. So here are my options. The key here is that I want the shapes to be congruent. So I want them to be the same shape and size. So that would mean that any type of transformation other than a dilation would work. So wherever I see a dilation, I don't want to use that option. So a rotation and then a reflection would work. That would keep the shapes congruent. Doing 2 translations in a row would work. Doing a translation and a reflection would work as well. So that would be my answer. In the next example, we have a problem like this. A figure is fully contained in quadrant 4. It is then reflected over the y-axis, reflected over the line y equals x, and then rotated 180 degrees clockwise about the origin. I want to finally know what quadrant is the figure in now. So what I do is I sketch out what's going on here, I do each process, and then I see what quadrant I end up in. So first let's sketch out some figure in quadrant 4. I just drew a star. So I'm in quadrant 4. I'm going to reflect it over the y-axis, which remember is this line right here. So I reflect it over. Now I'm in quadrant 3. Now I want to reflect over the line y equals x. Remember, y equals x is that diagonal line. Notice that that reflection line goes through the shape. So when I reflect over, it's not really going to move at all. Remember, think like a gymnast like flipping him or herself over on a bar. So I'm still in quadrant 3 after I did that. Finally, I'm going to rotate 180 degrees clockwise about the origin. So rotate 180 degrees, remember that's 2 quadrants over. So I ended up in quadrant 1, and I'm done. These problems are really difficult unless you kind of sketch out what's going on. So I'd highly, highly recommend doing that. And the last kind of problem we're going to look at is sometimes the hardest, so I saved this one for last. In example number 3, parallelogram ABCD is shown. Point E and F are midpoints of AB and CD respectively. Which transformation carries the figure onto itself? Now, we haven't looked at a ton of problems like this. What it means to carry something onto itself means that whatever transformation I do, it's going to end up in the same exact spot. So here are my options. Option number 1, I reflect across the line AC. So also option B, I reflect across the line EF. If I'm doing a reflection, that reflection line should be a perfect line of symmetry. So let's check AC first. While this might look symmetrical, remember that this is a parallelogram. So it's kind of like a diagonal rectangle. I'll look at it. Well, this cuts it in half. If I fold over, and we're going to look at an example in class like with paper, this would not be a line of symmetry. Like these, if I folded this over, this wouldn't end up perfectly onto one another. So reflecting across AC wouldn't work. If I try EF, same deal. This one might be a little bit easier to see. If I folded that parallelogram on that green line, they wouldn't end up being perfectly over one another. So reflecting over EF won't work either. Rotating 180 degrees about the origin, I'm going to end up in a totally different quadrant, so that's not going to work. Because remember, I want to end up in the same exact spot that I started in. The next thing that we're going to look at is rotating 180 degrees about the center of the figure. Now, what we're going to do here is like picture that I'm putting my finger in the middle of the shape, and then I'm going to turn it there. So it's not really going to move at all, it's just going to kind of spin about itself. So when I'm spinning it, it's going to kind of start there. Finally, when I do a full 180 degree rotation, I end up back in the same spot that I started in. So that's actually going to be my answer. And we're done.